Welcome. In this video, I'm going to discuss whether the sequence converges or diverges, and we're going to use the monotonic sequence theorem. But before we all do that, let's review. Remember, the monotonic sequence theorem tells you that every bounded monotonic sequence is convergent. Okay, so in order to use this theorem to show convergence, we need to show two things. One, we need to show the sequence is bounded. And two, we need to show that it is monotonic. And just as a quick reminder, monotonic sequences are non-increasing or non-decreasing. You can also use the stronger conditions of decreasing and increasing respectively. Okay, so for those of you in my class, if you still don't have this in your notes, please take a moment to put this information in your notes. All right, now that you have that information in your notes, let's show that this sequence is bounded. And I'm specifically going to show that it's bounded above. Remember, a sequence. All right, so the first thing we wanted to do is show that this sequence is bounded. So I'm going to show that it is bounded above by 1 and bounded below by 0. Let's begin with our sequence 1 over n plus 3 and consider 1 over n. Which one of these is larger? Is this one larger or is this one larger? Ask yourself about fractions you know. So 1/2. And now 1 over 2 plus 3. This becomes 1 over 5 and 1 over 2. And now which one is larger? Well, a half. Remember that a larger denominator implies a smaller fraction. And this is, of course, assuming the numerator is fixed. In our case, it's fixed at 1. Okay, so certainly 1 over n is larger. And now how can we show that 1 over n is always less than 1? Now for this, I think we can all agree that since we're starting with 1, n is always going to be larger. Because as we increase, we get n equals 2, 3, 4, etc. And I guess n could be 1 since we are starting at 1 in this case. It follows that if we divide both sides by n, we get 1 is greater than equal to 1 over n, which I can rewrite now as 1 over n is less than or equal to 1. Since there exists m equal to 1 in this case, such that 1 over n plus 3 is always less than 1, it follows that this sequence is bounded above. Okay, so now we've shown that it is bounded above by 1. Next, let's show that it's bounded below by 0. I think we would all agree that as the denominator is getting larger and larger, and the numerator is staying fixed, now here I'm going to abuse notation a bit, we end up with something like this, and that's going to be 0. Okay, so let's write out our conclusion. Since there exists m, in this case equal to 0, such that 1 over n plus 3 is always larger than 0, it follows that this sequence is bounded below. All right, so we've shown it's bounded below, so our sequence is bounded. All right, let's continue. Let's show that this sequence is either increasing or decreasing. And I think with our work we've done here, it's not a giant leap to say we're going to show that it is decreasing. Okay, so we're going to show it's decreasing, and I wrote here in this case, because for other sequences you might show they're increasing. So how are we going to do this? Well, we're going to do this with the derivative. So let f of x equals 1 over x plus 3. Clearly for integers n, f evaluated at n is just equal to our sequence. All right, so let's look at the derivative. of f, well, this is equal to the derivative of x plus 3 to the negative 1 power. All I've really done here is rewritten this. So this becomes negative 1 times x plus 3 to the negative 1 minus 1 power times the derivative of the inner function using the chain rule. In this case, it's just going to be 1. I could have skipped this, but I'm trying to be thorough here. And we end up with negative 1 over x plus 3 quantity squared. Now, this is certainly always less than 0. And if you don't see this, just consider that whether or not x is positive or negative, x plus 3 squared is always going to be greater than 0. If for some reason this became a negative quantity, we'd square it and we'd get a positive value. But now consider even further that it's never actually going to even be negative, since for n greater than 1, n plus 3 is always greater than 0. So we're always going to be positive. Okay, so clearly if I'm going to have something positive in the denominator of something negative, I'm going to get something that's always negative, and that's here. So this is less than 0. All right, so clearly the sequence is decreasing. Okay, let's recap what we've shown. We wanted to show that this sequence is bounded and monotonic. That is, it was either increasing, decreasing, or non-decreasing, non-increasing, respectively. We showed it was decreasing. And that way we could use the monotonic sequence theorem to tell us that it is convergent. The first thing we did was show that it was bounded above by 1, bounded below by 0. So it follows that the sequence is bounded. The next thing we demonstrated was that the sequence is decreasing. Now, since this sequence is bounded and monotonic, actually I should add that here, and it's monotonic, now we can write out our conclusion. Our conclusion is, since this sequence is bounded and monotonic, it follows that the sequence converges. I hope you found this video helpful without it feeling like pulling teeth.